Wow, I'm using up all of my luck right at the start here. Everything is going to go wrong, I'm sure. Um, but hey everyone, I'm Kimberly Wilber, and with me is Sagar. So we're software engineers at Google NYC. And it's a bleak day as usual in NYC, the land of pizza and late subways. But we have something fun to share with you, something that maybe you might not necessarily have seen before that we hope is going to be useful for the computer vision community. So we're making a data set of outdoor videos from a human perspective, and that data set is called SANPO. SANPO is quite a name, but it's actually the name inspired by the Japanese word sanpo, which is a brisk stroll. We chose it partly as a friendly nod to our collaborators at Google Japan, but also that's what this data set is, a bunch of outdoor videos from a human perspective. We're looking to publish the kind of videos that you might make if you strapped a GoPro to your face and went out on your morning run. And so why are we doing this? Well, there's two reasons behind this. First of all, is that it's of relevance to a project at our company that I'll be talking about. And secondly, it's because we want to push the field of computer vision outside. There's a lot of CV tasks that are adapted to mostly indoors. For example, I focus on depth estimation, and a lot of the best depth estimation data sets are indoor use, making it difficult when you want to estimate depth of pixels that are very far away. It's only recently that self-driving is beginning to tackle some of these tasks outdoors, but they're focused on cars which drive on roads, not sidewalks or fields, at least not if the self-driving is working correctly. But so as a platform, there we go. As a platform, we're collecting a bunch of videos by hand from volunteer runners. We have our own custom camera rigs, which I'll be talking about. We have two cameras rolling at every run. We have a head camera, a Z Mini. We also have a chest camera mounted with a custom mount that we designed ourselves that I'll talk a little bit more about. And then not just these videos, but we've also gone to the trouble of annotating each of these videos with several different kinds of labels that we hope will be useful to the community. For example, for depth estimation, we have both sparse depth. It's called sparse because not every pixel is assigned to a depth label. And that's from the Z cameras that we're using, estimated by their onboard depth estimation. And then we've also annotated these videos with ML depth from, oh, cool, it doesn't loop. That's all of the luck has run out at the beginning. We've also annotated them with ML depth from a fairly state-of-the-art disparity algorithm called Crest Stereo. And finally, the piece de resistance and the effort that Sagar has spent a lot of effort on is that each of these frames comes with or at least a lot of the frames come with hand annotated segmentation maps, which means that if you want to run object detection or scene understanding tasks, then that's going to be what you'll spend a lot of time looking at. So what can you do with a data set like this? Well, I've already talked about depth estimation. I've talked about segmentation masks. It's generally the whole idea is for scene understanding. So for example, another thing you can do with this is build 3D models of the world as seen from a runner's perspective. We have a fun little point cloud. But anyways, that's SANPO, an outdoor data set with tons of videos that researchers can use to understand outdoor environments. Oh, wait, but this slide is actually lying to you. The videos that I'm showing on this slide are not actually the videos that we took outside. These are actually synthetic imagery because we doubled the size of our data set by working with a third-party company called Parallel Domain to make synthetic data that goes alongside each of the real videos. But we'll get to that. Let's see. I'm starting to see a couple questions. These SANPO data sets are available for public consumption. There is a link at the very end, but if you search for SANPO on Google, you'll be able to find that. And indoor data sets of office room environments. Yes, there are a lot of really good data sets useful for various tasks. I'm familiar with depth estimation, and so I've spent a lot of time thinking about ScanNet, which is an academic data set where a student had a laser scanner on an iPad and they were walking around campus. And so they come with not just videos, but with like 3D models of the indoors. Unfortunately, this is not a maritime data set. We are not collecting it on the sea yet. Although, if I may go off topic, one of my colleagues at Google commuted to work via kayak, and so perhaps we could get him to help collect us for it, but that's a bit of a digression. So this is kind of an overview. And what actually motivates this data set? Like, why did we actually develop it? Well, before I tell you how we developed it, I'd like to tell you why we're developing it in support of a project at our company called Project Guideline. I work on the Project Guideline team, and let's see if I can seek to the right place. Yes. So Project Guideline is a very early research prototype, not meant to be like heavily commercialized, not meant to be like pushing state of the art, but rather it's exploring to see whether the devices that we have around us can help runners with vision loss go running unassisted. The idea is that lots of folks carry their phone around with them. Could we use that phone to help people with vision loss navigate and go running independently? In fact, I think I lost it. So the fellow that we're working with is called Thomas Pennock. He's the CEO of Guiding Eyes for the Blind, which is a guide dog organization in NYC. And so let's see if I can get the overview. You'll see him taking his cell phone and strapping it to a little harness on his chest. Okay, here's the example. So as he gets ready to run, he straps the cell phone onto his chest, and then the cell phone is looking down at a painted line. And then it's giving him feedback in the headphones. Like it guides him left if he hears sound in the left ear, and if it guides him right if he hears in the right ear. And it actually kind of came about because of discussions that we had with him. Like one of our team members was friends with him, and he kind of challenged us, like, for greater independence while exercise, can we make navigation for a blind runner possible? The initial prototype was very simple. It says on-device ML. It did not actually use ML. For just kind of the first hackathon build, we had a phone that was looking for yellow in the image, and it would just like surface that and see whether it was on the left side of the image or on the right side of the image, and that was enough to help Thomas run a event. He went on a marathon a couple years ago. But since then, we've sort of slowly been graduating and building this up into something a little bit more complex that maybe starts to push the frontiers of computer vision forward a little bit. So in particular, we collected a small data set of outdoor videos like the ones that we have, except these ones had like a line that we painted on the ground. Sometimes we had to like model the environment and paint it as a virtual polygon in like Unreal Engine to just get data set because there was nothing that we had for us. And it evolved into, instead of just looking for the line on the ground, looking for the yellow, a small on-device line segmentation program that is then fed into a slightly more complicated control system that can hopefully guide the runner around obstacles and at least have a sense of like where they're going. You can get pretty far without a very complicated setup, and so we want to be careful about how we add complexity here. Yeah, so this is sort of like from the phone's perspective. But Project Guideline kind of has limitations, of course. And these are limitations that we can't really easily solve at the moment. In particular, we want to build systems that can automatically avoid obstacles, that can handle noisy outdoor environments where the shadows on the ground can confuse the phone and get you running off track. You know, it's fairly important because if we mess up and if the system doesn't behave properly, then someone might like physically trip and get hurt. And another goal going forward for Project Guideline was to go offline. I know that many people know that Google makes products that require you to be online. Well, in the sense, this particular project requires the runner to be on a painted line on the ground. And so could we turn this into perhaps a little bit more general route planning system while retaining the ability to go running quickly? Um, so when we looked at kind of how do we get there, um, the overall goal would be like runner independence. But we need to build several different applications. Like we need the real-time guidance system. We need a system that does obstacle avoidance. We need a system that does route planning, and so on. These sort of high-level building blocks of something like Project Guideline. But each of these applications in turn build on top of tasks that the computer vision community, especially the academic community, has widely studied and widely discussed. For example, panoptic segmentations, where you get an image and then you see for each pixel what is the class label of that image. Is it a trash can? Is it a road? You need a good like real-time panoptic segmentation. Another thing, my specialty is like depth estimation. You need to understand where you are. And then you might imagine like other things like localization mapping, typically called SLAM. But at the bedrock of each of these is to have data sets that match what you're doing and to have careful evaluations. And so this is what I'll sort of be talking about, kind of our efforts of building SANPO as kind of the data set for this. A question about privacy. Yes, the information is filtered. I have a couple slides on that. But the executive summary is that we blur faces and license plates. Now, we thought about why go to the trouble of commissioning a data set from our team's funding budget. And there's a lot of outdoor data sets that sort of get there, but aren't quite as useful for our application. For example, there's a lot of excellent work happening in self-driving, and real-time self-driving systems are getting there, getting more accurate. However, whoops, yeah. However, the domain shift from self-driving to sidewalk navigation is a little bit tricky. Like if you're a car and you're avoiding obstacles, the obstacles that you see are the cars in front of you and stoplights and stop signs. But if you're a runner running through a park, there's no cars, but there are bushes and there's fences and there's different kinds of ground terrain. So these data sets don't necessarily capture each of the sorts of annotations that we wanted to collect. So we kind of had to home grow it ourselves. And so we were off. We started in kind of early 2022, I think, planning this what turned into a very large and sprawling data collection effort. In particular, we designed our own collection rig. You can sort of see pictures of it. And there are two pieces. I'm going to talk like at length about the details here because I think that that's what's most interesting. We have like a 3D printed harness that clips to the runner's chest using like one of our friends from the Google Maker Labs had a 3D printer and some expertise, and he like was purchasing bulk rolls of elastic banding off of Amazon and then cutting them into pieces and then shipping it to our office with inter-office mail. It was a really fun phase of the project. We were thinking about like how do we build a rig that can take multiple views of data. It's a lot of data to process in real time. Like because we have we wanted a stereo data set, but we also wanted a multi-view data set. So because we have this head-mounted Z mini camera and a chest-mounted Z2i camera, as they're recording, you need a system that can process all of that data. And so the company that makes these cameras, Z, has what they call the Z box, which is a box that has like enough ports to plug everything into. So we had to like figure out how to find a battery with the capacity to keep this Z box running for a couple hours at a time, and stuff it into a backpack. And there were many meetings where we were talking about like the cooling of the backpack. The device is getting too hot because it's just in a runner's backpack. And so we had to like hand design, the fellow who worked on that had to hand design like a 3D printed cooling fan that sort of sticks out of the backpack. It was a really fascinating aspect of the project. Um, let's see. Yeah, and so then we went running. We sort of put a call out to a couple mailing lists for people inside the company, and we recruited maybe 10-ish, maybe 5 to 10 volunteers to run at several different areas inside the states that they lived in. Um, I'm missing a slide. Oh, I skipped the slide. I went back and forth on this. We called it the Ghostbusters rig because it sort of looks like the goggles that the fellow from Ghostbusters wore. But that's neither here nor there. Um, one thing I do want to talk about, and what was asked as a question, is that when you're going outdoors and filming people, you have to be careful. So that's why our data collection had to be taken kind of in concert with the privacy teams at Google that influence product decisions. In particular, there were lots of local laws to follow about how we allowed people to opt out. You know, if your data is represented, you can send us a line and we'll remove that data from you, no questions asked. We also have we put together some tools from around the company to blur faces, license plates, and other identifying information. So hopefully that allows us to collect data in kind of a responsible way. We were also sort of concerned a little bit about the diversity, not necessarily of people, because we don't, this isn't like a data set of people per se, but we cared about the diversity of the environments that were featured in the data set. And so we kind of collected data in batches. And so before planning on going to collect a batch of data, we first processed all the data we had, put it into a giant spreadsheet and decided where to go running next based on what obstacles were overrepresented in the previous data. However, of course, the data is fairly USA centric, unfortunately. Um, just a moment. I will save some of these for the very end. I think I'll address those at the very end if that's all right. Um, so the data collection, now we have 4 video streams of raw RGB images. We have 4 of them because we're using 2 cameras, and each of those cameras has 2 lenses. And so how do we annotate that? First, I'll talk about annotating for panoptic segmentation. I guess I don't necessarily have an example. Yes, I do. So panoptic segmentation, the task is to label every pixel with 2 things. Firstly, what kind of thing is it? Like, is it a car? Is it a tree? And then secondly, each pixel is also labeled with a unique instance ID. And the reason why we need that is because, for example, there are 2 cars in this image. And you can see that in the map, they're separated out because we've been able to say that this is car number 1 and this is car number 2. The computer vision community has thought a whole lot about how to do segmentation efficiently. And basically, most data sets that you see that have been annotated use kind of this combination of a human annotation, which you very muchly need to ensure quality and accuracy, and also machine learning annotation, which you very muchly need to cut down costs on shoestring budgets like ours. So after a bunch of trial and error, we narrowed it down to splitting up the annotation effort. So we did this in 2 ways. First, we made it easier temporally by subsampling. So we only annotate the image quality. I think it's every 5th frame. Sagar can correct me if that's wrong. And we used a system called AOT to propagate the previous segmentation maps from one frame to the next. And then the second strategy that we used to break down annotations was to partition the labels that we wanted to annotate. So we have this taxonomy of maybe 20 objects that was inspired by Cityscape's taxonomy. And so we first started from the objects that are easy to label, and we sent those to a rater. And then when we got the results back, then another rater would take the objects that were harder to label, and they could see the first rater's annotations and they could repair them. And then they would continue, and then this would sort of keep going until all of the 20 labels were annotated. And when you do that, there's a lot of human error in the sense that like people might not necessarily agree on things, people might not necessarily know how to label them. So you have to sort of be careful about how you counteract that. We counteracted that by having very careful instructions. You know, this is a fence, this is a pole, this sort of wide pole. You know, how do you handle that? And the second thing is that we sort of drove this very interesting real-time consensus where as each of the annotators were annotating, they were also sitting in a conference call, muted with their screen off and their camera off. And anytime someone was like wondering about a question, they would unmute themselves and go, "Hey, everybody, can I get a second pair of eyes on this?" And they would show the example that they were wondering about. And then you could just get you could sort of everyone could talk about it and they could choose the label that made sense in terms of everyone sort of being unanimously choosing the label that they made. And however, this is not necessarily like, you know, pixel perfect. And I'll get to our solution on pixel perfect annotation quality later. So that's why we provide information about which frames were labeled with AOT and which frames are human labeled. We kind of want this to be extensible because later on, there are going to be depth estimation algorithms that are better than Criterio and segmentation that are better than AOT. So we publish the stereo data, even though it doubles the size of the RGB frames, so that people can use whatever better comes after Criterio or AOT at the very end. But we're pretty pleased with the results. This is on par with other data sets as well. And then I know I'm almost out of time. Actually, let me check questions. AOT, yes, see, that is Sagar's thing. And AOT refers to a paper that is a machine learning system that, given a previous frame and a previous mask, and given the current frame, AOT looks at which pixels are moving from the previous frame to the current frame. And then it takes the mask and moves the mask labels from the previous frame to the current frame. The idea is that if AOT is working well, then the next annotators who are looking at later frames in the video only have to worry about sort of the labels near the edges of object boundaries. I wish I had included more information, but it's a paper that you can look into. We sort of used off-the-shelf system. Depth was a real challenge. And the reason why this is a real challenge is that depth is kind of something that works well for indoor cases, but not outdoor, for two reasons. Firstly, the way that depth perception on humans works is that you have your two eyes and you look through them. And if objects are very far away, such as something that's outdoors, then they're going to be very close in your field of view. So we're talking like subpixel accuracy needed to accurately estimate depth. The second issue is that LiDAR, which is typically a system that's usually used, doesn't necessarily work so well outdoors, especially the consumer LiDAR systems that you get on various cameras that we were considering. And so Zed has their own system, which estimates what is called disparity. There was another question about the difference between depth and disparity. Depth is at each pixel, how far away is this pixel? So the ijth pixel in the image might have a depth label of 10 meters, saying that's 10 meters away. Disparity is what people use. It's sort of an intermediate processing step that you can turn into depth. Disparity is the difference between two images that have been rectified. So for example, on the top camera here, we have a left image and we have a right image. And then the sparse depth map is proportional to the disparity, which is like how many pixels across has the object slid, which corresponds to how far away it is. And we convert this disparity map into depth. as kind of a pre-processing step. However, often it's an older system, and so it doesn't necessarily work well. So we had a bunch of trial and error to land on Cresterio, which is an algorithm that takes two images and then just outputs disparity maps that we convert into depth. Before we leave, I do want to very much talk about synthetic data because this was a huge part of the data set. We worked with a third party called Parallel Domain. And Parallel Domain is a company that specializes in creating synthetic data for especially self-driving car situations. The idea is that they work with companies to make tuning their machine learning systems faster. And we were interested in working with them because we wanted to study this transfer learning task, which is, can we use synthetic data to improve model performance in the real world? Like, we can straightforwardly double the size of our data set with synthetic data that honestly looks pretty great. And perhaps that translates into real world performance. And it does, especially so in depth. But people can look them up. Basically, the workflow that we had was it was this interactive back and forth where we talked about like the taxonomy of labels that we wanted to annotate, and then we went back with them in batches to get results, and then we would run experiments to see how well that previous batch improved the models that we were working with. I am out of time, so I'm not going to talk about too much for that. But to give you a taste of how high quality these images are, I had the previous slide, but there are some of these that are real and there are some of these that are synthetic. And you might not guess that these are the ones that are real and synthetic. I was going to do this thing where we pause and I could like ask you for each one, but I don't know that that works well in the live format. So yeah, we've wound up at a data set with lots of real images, lots of synthetic images, annotated labels for 20 different classes, annotated depth, and each session has two different cameras with two lenses each that we hope will be pretty useful. Honestly, that's probably an appropriate place to stop. So I make it sound like it's easy, just a small piece of work, but honestly, this is a huge team. And I'm so incredibly privileged to be a small part of this data collection. So yes, if you're interested in downloading the data set, you can do that there. We have details about machine learning experiments that we ran with this data set in our paper, which is on arXiv. And so I am happy to take questions. Let me go ahead and take a look at some of these questions. So this one question, let me take a look at this. James, maybe if you could contact me after. My email is kwilber, that's my last name, at google.com, and then we can talk about this this robot operating system that you have. Like, we've looked at a lot of robotic data sets that are used for robots, and so that would be very interesting. Nicholas asks, how can we help with diversity and international expansion? That's another important question. In terms of international expansion, one important limitation is that it's USA centric. I think that we sort of have to do that, we would have to open up outside volunteers to help. And so maybe in the future there could be a system where like other people can help contribute, and maybe we could publish the rig that we used, and the protocol, and you could send us data from other countries. But I admittedly don't think we have a great answer for that at the moment. James asks about event cameras. I agree, event cameras are really great. In fact, the problems with the cameras that we have can be that motion blur becomes an issue, resolution becomes an issue, and especially dynamic range of the images becomes an issue. We had to throw away a couple samples because we captured them in twilight, and the difference between the black and white pixels was just so much that we had to discard the samples. So maybe event cameras could help with that. Um, the name of the paper is Search for SANPO. It's on arXiv SANPO dataset. When studying depth, can you show what we settled on after sparse data? Yeah, sure, I can. We tried a couple different approaches. I only have one example, sadly. But crest stereo is the name of the algorithm that we took. Now, I am of the opinion that it works better on the chest camera because of the resolution difference. The head camera is the Z mini camera, and you can see the depth quality is not quite there yet. However, there's a couple recent advancements in the field. I'm interested in Zoe depth, which is a monocular model that I want to say Intel put together. That might be a more useful baseline. And then also is a recently highly publicized depth anything model that I would love to see if it gives better quality on this work. So yes, I think I will end that here. And thank you for your time and attention.